put a challenge problem up there. Going to say more about that in a few minutes. This is the little recap of where we've got to. So looking at total angular momentum, keeping our notation straight in our heads, RG, center of mass. The little r's are position vectors from points in the body from the center of mass, and the big R's are those same points measured from an inertial frame, right? So when I take my big R dot, which is I need the big R to describe the total momentum, needs to be from in the inertial frame. We use this derivation of Ri, little r dot, Ri dot is omega cross Ri. Then we did some tricks and we got to this form where I pull out the omega and I end up with a matrix times omega, and it's made of things that look like this, which I want to say more about. And then we rewrote it in dot product form. There was a typo at the end of the last lecture. There should be ij here and i's and j's there. So this is the ijth component of this inertia tensor. Okay. Let's see if we can make some intuition for what's going on here. So if I look at this expression Lg equals Ig omega, and Ig is made up of things like this matrix A squared. What is it informing me? What information is living in there? Well, it's got the mi there too, right? And I'm integrating, I'm summing. I'm going to turn this into an integral in a moment, in a continuum limit. It's really telling me the distribution of mass around each axis of rotation. And in a sense, you might think it's something to do with like how hard it is to rotate about a given axis. Right? So for instance, I don't want to lose that board, so let's come over here. Compare. And looking at that A matrix, we'll just focus on the diagonal terms, right? Those are the most important ones, well, at least in our context. Let's suppose I have a cylinder. I'm going to draw two different cylinders. Okay, so let's call this cylinder little 1, and cylinder 2 is going to, suppose it has the same total mass, but it's a bit wider and shorter. Okay? So when I think about linear momentum, P equals m times rg dots, they have the same m, right? Which means that in terms of accelerating this object in a translational sense, it's equally hard to move either cylinder, right? So the question is, how would this Ig matrix compare for one cylinder versus the other one? So if to define this matrix as a matrix, I need a coordinate system. So let's call, the only one I really care about is the axial one for the sake of our argument. So let's call that direction E3, and we'll do the same thing over here. And I claim, and I think you'll see this is not, I'm jumping ahead a little bit in that those formulas are sums over a finite number of particles. And I guess I could imagine a cylinder as being a large number of finite number of particles, but it would be more natural for us to turn those sums into integrals and that mass into a density. I'm going to do that in a moment, but I just wanted, okay, so bear with me. This is, instead of a sum over m's, imagine it's an integral over a rho times those same quantities. Okay? So my claim is that if I write the inertia tensor for this picture here, that it's diagonal in that coordinate system, because I'm using the symmetry of the cylinder is basically why. And indeed, it's going to be it will have two equal elements here, and that's because the E1 and the E2 direction are equivalent. The only thing that's different is the E3 direction, and so it has the form of AAC. Okay? And zeros on the off diagonals. And IG is going to be the same thing in this scenario too. The only thing that's going to change is the values of the A and the C. So IG2 will also have that form. We'll call it A2, A2, C2, and then zeros. So can anyone see, looking at the form, sorry, I feel like I've used slightly awkward notation again. That A is what's composing this matrix, and this A is what I'm saying is the first diagonal element of that matrix. So it's a different A. I want to focus on the C. What can we compare this value C1 and this value C2? Can you see which one of those would be larger in cylinder 1 versus cylinder 2? So it's this term here. Right? I'm adding up the contributions of x1 squared plus x2 squared. But x1 in this coordinate system is the variable associated with one of my E1, which is in the cross-section of the cylinder, and x2 is the other direction in the cross-section of the cylinder. So when I say that this thing is giving me information on the distribution of the mass, in particular, the more spread out the mass is in those two directions, the larger that number is going to be. So you can sort of see the wider cylinder has more mass at larger values of x1 and x2. It's going to have a larger value of this C. See that? So add, if you want, this is the x1 direction, that's the x2 direction. Okay? So C2 should be greater than C1. Okay, now I want to imagine that I take the cylinder, I rotate it on that axis, its long axis. Okay, so let's find an axial vector omega, which we'll say omega E3. Right, so I'm spinning the axial velocity only around that axis in both cases. So our derivation there tells me that the angular momentum, the total angular momentum, is this matrix times the angular, times this omega. Right? So since omega is only having an E3 component, when I take this matrix times omega, that means this matrix times the vector 0, 0, omega, and I just get C1 or C2. Right? So LG1 is just going to give me C1 times scalar omega E3. And similarly for LG2. So if, two ways to think about it, suppose the omegas are equal, right? So I'm spinning each cylinder exactly the same angular velocity. This fact, I have the mass is spread out more in the cylinder on the right, means that LG2 is going to be larger than LG1. Or another way to think of that, LG, the balance of angular momentum says that LG dot is whatever external torque there is. So you can think of it, I need more torque to get the cylinder on the right spinning at the same rate as the cylinder on the left. Right? Or another way to think about it, alternative view, is suppose LG dot is 0. And this is not strictly speaking fitting within rigid body, but suppose that as LG dot is 0, I change the distribution of mass. Okay? So that C goes down. Right? What I'm imagining here is an ice skater. An ice skater is doing a spin, right? So they're spinning. Suppose there's not much torque. And the ice skater tucks their arms. Right? They're spinning around that axis. More mass outward. Tuck the arms. I'm bringing the mass inward, which means the x1 squared plus x2 squared goes down, which means that element C goes down. LG dot is 0, so LG isn't changing. But C has gone down, so what happens to omega? Omega goes up, right? Which is what happens. Ice skater tucks their arms, spin faster. So IG is the thing that's connecting angular momentum to angular velocity, and it's a tensor or a matrix because it depends on the axis of rotation. So it's more complicated than linear momentum. All I need is a mass for linear momentum. Angular momentum depends which axis you're rotating about. The challenge problem I've put up there is called the intermediate axis theorem. And the idea, actually it's an experiment you can do with your phone. So a phone has sort of 3 key axes, and they're all different lengths. So the 3 diagonal elements of the inertia tensor, if I orient those 3 axes on the main axes of the phone, are all going to have different elements. That's going to be the largest one, that's going to be the smallest one, and that's the intermediate one. Intermediate axis theorem says that if you start an object rotating around one of those axes, the largest and the smallest axis, the rotation will be stable, and the middle axis is unstable. I'm not going to do this experiment here, although I have a reasonably good phone protector. Try this on a sofa. Set your phone spinning. If you spin it this way, it reasonably stays spinning on that axis. If you spin it this way, it's a bit hard to do like a helicopter, reasonably stays spinning on that axis. If you spin it this way, on the sort of intermediate, so I'm spinning it about the intermediate axis, it wobbles, so it doesn't stay, that rotation is unstable. Showing that is, I'd say non-trivial, but it is within the skill set that we've been building. It's an instability problem. You can do it as the sort of tools. It's thinking carefully about an LG dot equals 0 and what that means in terms of a stability problem. So 2 more things I want to do with the generic version. One is, what are those off-diagonal terms doing? So to summarize, the diagonal terms tell me how hard it is to rotate about each axis, right? This term right here describes rotation about the E1 axis, and you see that it only cares about x2 and x3. Those are the directions orthogonal to E1, how spread out the mass is from that axis. And same on those 2. The off-diagonal terms are a bit weird. The short story is they couple rotations. So if they're present, so in my little calculation up there, if it's a diagonal matrix, a tensor, inertia tensor, and I have a rotation about one axis, my angular momentum is only in that axis as well, right? If I have off diagonal terms, that's no longer true. You multiply, you might have an angular momentum around one axis, angular velocity, sorry, around one axis, but you get an angular momentum that involves other axes. In short, you might imagine that that comes from asymmetry in the distribution of mass. So if I had something like a cylinder, and then the cylinder had like a bulge, I no longer have the nice symmetry, and if you work out the inertia tensor for that, it has off-diagonal terms. Or I could have a symmetry in my system, but if I choose my axes in a, I don't know, sort of wonky way that doesn't respect the symmetry, again, you get off-diagonal terms. For the most part, we won't worry about those. And one of the reasons we don't really usually never need to worry about those is from linear algebra. I think you've seen that if I have a symmetric matrix, that I can diagonalize it. A squared is symmetric, which means there is a basis under which it's diagonal. So I can always reduce the angular momentum to a diagonal tensor in a particular basis. So for us, those off-diagonal ones we mostly won't worry about. They're messy, and we know that in principle we could get rid of them. So let's just make a quick note. Lin alg 2. I is symmetric. Okay. So we'll basically focus on the diagonal terms. And the other thing I've said, and now let's write it down, is it's a bit clunky to be talking about sums. I want to start thinking about physical objects, and physical objects are much nicer to express as continuous objects. And so quite straightforward to take all the development we've been doing as a sum over little point masses and turn it into a continuum. So I go from a system of particles to a continuous distribution of mass, right? So let's just make a little table. Here's the discrete quantity, and here's the continuous. In the discrete version of our development, we've had a mass, some little point masses m sub I, and those turn into a density. So you can think of that's like a rho. Rho, if the m's are not equal at every point, the rhos can be a spatial field, right? So that's rho of r. And if I want the actual mass, then I get times a little delta v. I can take a density times a volume element, you get a mass. Right? So we had capital M, which was the sum of m sub i's over all the system, and that turns into an integral of the density over the volume. So sorry, let's write it. Rho is a density here, meaning mass per volume. And then we have our actual inertia tensor is made of this sum of m's times these a sub i's. So minus m sub I ai squared. And that's just going to turn into, it's not going to fit in that space. Let's put it down here. An integral, I'm going to write this in a slightly funny way. So my inertia tensor in the continuous limit is an integral over the volume of the body, because there's a sum over all the points of the density, which I'm just going to pull out, and this is an integral of a matrix, so the answer is a matrix, of this exact same form, right? So I won't write all the off-diagonal terms because it gets messy. x1, x2, and so on. Okay. Let's have a look at energy. In particular, how does kinetic energy translate into this system view or continuous distribution of matter? So we need to start from what we're sure about, and that really means capital T is what we've been using for kinetic energy. The kinetic energy, let's do it in the sum form, and then you'll see how it can translate to an integral. The kinetic energy of the system is just the kinetic energy of each particle, and the kinetic energy of a single point particle is 1/2 the mass times its velocity squared. We've been using that the whole time, which means that my total kinetic energy is the same as a sum of 1/2 times the mass times the velocity squared. But again, being careful that I measure velocity in an inertial frame, which means I'm not using those little r's, I'm using the big ones that are measured from inertial frame. So it's 1/2 mi r, big R, I dot squared. Oh, that if you want. Okay. So now the question is, that's very messy. How do we break things down into a nicer form? So Ri dot squared, well, Ri dot is Rg dot plus little Ri dot, and little Ri dot is omega cross Ri. That's where angular velocity comes in. So this is equal to 1/2, pull that out front, I guess, sum mi. So I get an Rg dot, and then I'm going to square that, so I get an Rg dot squared. I get 2 copies of Rg dot omega cross Ri. And then I get the Ri dot has omega cross Ri dotted with itself, so plus in plus in omega cross Ri dotted with itself. Let's write that as squared. Oh, fine. Okay. This term looks nice. This just looks like the kinetic energy at the center of mass. That's what it is. This term and this term we need to do something with. The middle term, so the key to the middle term is that Rg is independent of our sum over the i's. Omega is also independent of that sum. So the only thing that's seeing the sum is the m sub I r sub I, but we saw the last time that the sum of m sub I r sub I is 0 because it's the center of mass. So you can pull those two things out of the sum, and the sum sums to 0. So this whole term is 0. And again, that would not have worked if we were not at the center of mass. Okay, so now we need to do something with that one. And need to pull some vector identities out of our hat. So one thing, we can write that as Ri squared omega squared minus Ri dot omega squared. This is one of these scalar quadruple products. You proved this in geometry, I think. And I'm using squared to mean Ri dot Ri. Okay, that on its own is not super helpful, but if we recall, we play around with this definition a little bit. So recall LG is our sum Mi somewhere in getting to that form there, we had this step written this way. And what I'm going to do now is write that vector triple product using another identity from geometry, which is that that's the sum Mi Ri dot Ri omega. So it's Ri squared omega minus Ri dot omega Ri. Again, sum over I. And here's the trick now. If I compare that and that, this is just a dot product with omega away from that. So a dot with omega, the first term gives me an omega dot omega, second term gives me a second Ri dot omega. So therefore, kinetic energy is 1/2, and of course this first term here has a sum over the m sub I, so that's just the total m. So I have 1/2 big M Rg dot squared, which is what I would have expected the kinetic energy of the translation, right? So 1/2 M Rg dot squared, and then there's a portion of the kinetic energy that comes from rotation, and that is so Lg dot omega. And you might notice they look slightly different. Actually, they're the same form, right? Because capital P, the total linear momentum, is what? Capital M times Rg dot. So this is 1/2 P dot Rg dot. And this is 1/2 Lg dot omega. It's the same thing, right? Total momentum times the velocity, total angular momentum times the angular velocity. Sum of those two, total kinetic energy. Okay. So what I'd like to do is work through an example, and let's just kind of summarize where we're at. The mechanics of rigid bodies. We've worked it down to two equations. One balance of linear momentum, which says that m times rg dot dot is, which I can also write as p dot, total momentum, is equal to the external force and we'll just write it that way, meaning that if there's more than one, we sum them. And now we couple that to Lg dot, which is d dt of I g omega is the total torque. And that's a complete picture, right? That's 6 degrees of freedom. If you give me those external forces plus whatever initial conditions, 6 degrees of freedom, 3 in Rg, second order equation for Rg, 3 degrees of freedom in omega, and it's a second order equation. Yeah, omega is already a velocity, so it's a first order equation for omega. As we'll see, this usually reduces to a second order equation for something like a rotation angle, and that's the example I want to do now. So if I solve that sixth order set of equations, and notice, of course, that these certainly can be linked because Rg might be living there. If I solve this and I have omega, so given omega, I get the orientation of the body comes from so really you can solve that, but you might need to also, if you want to know the orientation of the body, because the torques might depend on the orientation of the body, this is also linked to the fact that the vectors living in the body, the non-inertial frame, they change according to that cross product. Okay? Okay, let's see if we can work through an example. So system I have in mind is a cylinder on an inclined plane. So cylinder's coming out of the board. It's on a plane. It's going to roll down. And the key is I want it to not slide down, but roll down the plane and see if we can work that out. Okay. I think probably the hardest thing in these problems is setting everything up and seeing all the different coordinate systems and so on. So let's see if we can do this carefully. So let's start with an S hat frame, an inertial frame. And the way I'll do that is let's call this, I'm going to put the origin at the center of mass at the start. Okay, and I'm going to call that the E1 hat direction. E1 hat vector, and let's use x1 hat as the variable for how far the cylinder is moved in that direction. And we'll call this direction pointing towards the ground as the E2 hat direction. And what I'm really doing is putting my origin at the center of mass, right? So I'm however far the thing extends in or out of the board, I'm putting it at the middle. And then I also have a frame that I'm going to put in the cylinder. So let's redraw. And let's choose so I have, again, an E1 pointing that way and an E2 pointing that way, but that's at T0. So imagine before the cylinder starts rolling, I have a little blue dot there, and I'm saying the E1 direction should always point towards that blue dot. Okay? So E1 is going to move as the thing rotates, while this E1 hat is always going to be pointing down the hill. That's my inertial, that's the non-inertial in the body frame. So just add to our picture, if this thing rolls a bit at some later time, t greater than 0, what we'll see is that E1 is no longer pointing the same way. E1 is now pointing like that, say. And what we'll do is we'll keep track of how much E1 has rotated by measuring the angle between E1 and E1 hat. And let's call that theta. Right? So as it starts to rotate, E1 is going that way, and we'll call that theta of t. We also need to keep track of how far it's gone down the hill, right? So let's call, we have that as the x1 hat variable. So let's call this distance x1 hat of t. Okay? So maybe keep this where we can see it. So on the one hand, I can relate x1 hat to theta, right? Because however far the thing rolls, the circumference must be tracing out x1 hat. That's specifically what we call a no slip. So if it's not slipping, and no slip means that I can't slide down the hill. If I'm going down the hill, I have to do it rotating. So if no slip, then I see that there's a connection that x1 hat must be the radius of the cylinder times theta, right? So I haven't given a name to that, so let's call the radius A. And notice that in doing this, I'm not restricting theta to 0 to 2 pi, right? If it keeps rolling, I'm letting theta just keep on going. Okay, we need an inertia tensor to do balance of angular momentum. And it's a cylinder. The inertia tensor is going to be symmetric. I've sort of said that that comes from symmetry. You can kind of see it from symmetry. You can also just do the integrals, right? Do those integrals in polar coordinates, and those off-diagonal terms, due to symmetry, they all go away, right? So the inertia tensor is diagonal, and in fact, I don't care about any of the terms except the one that tells me about rotation about the axis that it's actually rotating about, which is the E3, right? This is E1, E2, E3 is pointing into the board here, right? So basically the inertia tensor has some term there that I don't care about, some term there I don't care about, and a term here that I do care about, which I'm going to call I33, and zeros everywhere else. And for now, let me just write it as a claim. We'll see if we have time to say more about it. I33, Okay, so that's the integral over the cylinder of the density times x1 squared plus x2 squared dv. We're going to suppose that the cylinder has constant density and total mass m. Oops. And that means that the volume times the density is m, and the volume of the cylinder is pi a squared times the length. So m is rho times pi a squared, times the length of the cylinder L, which means you can write rho as m over that, put it in there, convert this to polar coordinates, and I'm not going to do it on the board, but if you go through all that, in fact, that's in the problem sheet 7 or 8, possibly 7, what you get is I3 is m a squared over 2. Okay. Got an inertia tensor, angular velocity. It's only rotating about that E3 axis, right? So omega is of the form 0, 0, omega 3. And I claim that omega 3 is theta dot. This kind of fits things we've seen before, right? Theta dot is how quickly the thing is rotating, and the rotation is about that axis. If you want to prove that, what you can do is work out the change in E1 and E2. So E1, the way I've set it up, is cosine theta E1 hat plus sine theta E2 hat. Which means that E1 dot gives me a theta dot, and I'm going to skip a step. You can verify the intermediate step. E1 dot is theta dot, plus I get a minus sign here and a cosine here, and I can write that as theta dot times E3 cross E1. But by construction, E1 dot is omega cross E1. That means that omega is theta dot E3, which is what I've written here. It's also worth convincing yourself that theta dot, that this should be a positive and not a negative. And the way to think about that is if I have my right thumb aligned with E3, so E3 is into the page, and theta increases, is that a positive rotation, right-handed rotation? Right? So theta's, the E3 is that way, theta increasing is that way, and that is the rotation of the cylinder. So if I had E3 coming out of the page, it would be the opposite. It would be minus theta dot. It's always, it's getting used to this right hand using the thumb trick. Okay. So let's see if we can put the pieces together. So if I write down balance of linear momentum, my center of mass, Rg, is just x1 hat 0, 0 in that inertial frame. So linear momentum says that mRg dot dot is F external. And what external force do I have in this system? Okay, it's rolling, so it's gravity. Gravity is minus mg. Put that as a vector for the moment. And then here's the tricky bit. I'm going to leave this as a plus maybe other stuff. Probably thinking there's a reaction force. There is a reaction force from the surface. In fact, there's another force we need to be careful about. So let's leave that for the moment. If I write down angular momentum, so well, it says LG dot equals tau external. And really what we've reduced it to, so LG is IG omega. Omega just has an E3, which means all I'm going to pick up is this term. Oops, this should be I33. So this is the equation I33 omega omega 3 dot, but that's theta dot dot equals whatever torques I have projected into the E3 equals tau external. Okay, so it's really about figuring out other forces in the system. So on the one hand, we have a normal reaction, but it's not doing anything. I'm trying to think torques, right? Torque, by definition, is the lever arm from the center of mass, that's where I'm doing balance of angular momentum, cross the force. So there are three forces in this system. There's gravity. There's a normal reaction, right? The cylinder is pushing on the surface is pushing back. But gravity is not going to create a torque because torque is it's like R minus X cross F. This is the center of mass, right? XG if you want. And this is where the force is being applied. So the force is being applied at the surface. Center of mass is right there. North, so N creates no torque because it's aligned with RG minus N. Sorry, minus XG. R minus X RG. So N creates no torque. We have gravity, but gravity creates no torque at the center of mass. We've stated that before. As I said, you can think of gravity as acting on the center of mass of the rigid body only. But if it acts on the center of mass and I balance angular momentum about the center of mass, then it's doing nothing to rotate the body. So gravity is not creating any torque in that equation. So it sort of looks like there's no torque. So why does the cylinder rotate? You must be missing something. And what we're missing is that a cylinder will only rotate if there is in fact friction. Think of put a cylinder without any initial rotation on a perfectly smooth, icy surface. It doesn't roll down the surface, it'll just slide down. The only thing that can cause a rotation, it can't be the normal and it can't be gravity, must be a friction. So we've spent most of the term getting rid of friction, but if I want a cylinder to roll, I need to add friction. And friction, which way is it acting? So the cylinder's moving that way, friction is acting uphill, right? So that's, call it, say, F equals So it's in the minus E1 hat. So call it minus little f E1 hat. Okay. So finally, we can complete linear momentum is mx1, slightly ugly x1 hat dot dot, is gravity projected into the E1 hat, which is mg sine alpha. The normal reaction doesn't appear here. The normal reaction is just balancing the fact that it's not moving in the E2 hat. So I also have the friction force, which is pointing uphill, so minus F. And then I have I 3 theta dot dot equals this is the torque due to the friction. This is the vector that points from the center of mass to the contact point. So you do that cross minus FE1, and you get a torque that looks like E3. So this is going to be A F E3. Few subtle steps, I think. Study this carefully to make sense of these. But that equation plus that equation, two second-order equations for the two variables that describe the orientation and location of the cylinder. And the only problem is they both have this mysterious friction force, which I don't know. On the other hand, x relates to theta. We already said x is a theta, so I can relate these two equations via that. And I can also eliminate the f. Sorry, this is just like, that's dot E3, so this is AF. I can eliminate the f between the two equations, and I get a single second-order equation. So use x1 hat equals a theta, so x1 hat dot dot is a theta dot dot. Eliminate the f, and you get a single equation, which I'll just write, and then we'll have to stop. I'm going to write it in terms of x, but you can do it either way, which comes out as m plus I3 over a squared x1 hat dot dot. mg sine alpha. There's no x's over here, no variables over here. This is just a constant. So in fact, this is a very straightforward equation, just second-order equation to solve. That's not surprising, because in terms of the center of mass, it looks like it should just be falling down the hill under gravity, but gravity gets the sine alpha because the hill is at an angle. But then you can work backwards and work out the rotation via that. Okay, let's stop there. Thanks. Okay, shall we get going? So that's the system we were looking at. Cylinder radius A is rolling down a slope. By the end of the last lecture, we got to a single second-order differential equation for this variable, doesn't look very good, which is x hat, the displacement in the direction of the slope. And that came from writing linear momentum, which was reasonably straightforward, except for this extra friction force. And we realized we need the friction force because when we think of angular momentum, there are three potential sources of torque. And this is just to clarify that picture, because I think this is probably the bit conceptually that's maybe hardest to grasp in these problems. We're doing angular momentum about the center of the cylinder. So gravity does nothing in terms of a torque because it's acting at that center of mass. Right? I need a lever arm to get a torque. Normal reaction force, the surface is pushing back in the normal direction of the surface. That creates no torque because the vector, the lever arm, is pointing the opposite direction. So those two observations led us to think, if there's not another force out there, then it's not going to roll because there's nothing creating a torque. And so we add a friction force, which is acting uphill. And then if you do that cross product with the lever arm, you do get a torque. And then we have to be careful that same friction force is also going to act on balance of linear momentum, and then our resulting equation came from removing that F, the unknown F, from both of those two equations. And at the very end of last lecture, I think we got to this equation, which is, so in a simplified form, it comes out as 3 halves mass times x hat dot dot equals mg sine alpha. Okay. And of course, we can solve that. Once you solve that, you can connect to a theta. Okay. I see we're going to hit some groups here. Let's talk about energy. And I'll move over here. And the interesting thing about the energy is because we've added a friction force, you kind of think energy is not conserved, right? Friction is what we normally think of as removing energy from the system. But that turns out not to be true. And let's show that. So we have two, we think about kinetic energy and potential energy. The potential energy is gravitational. And if you recall, if I have a point mass under gravity and it's at height z, the potential energy is just the mass times gravitational acceleration times z, at least in this uniform gravitational field. We've seen that before. So if we want to work out the potential, the gravitational energy of the solid cylinder, we imagine extrapolating that to a uniform density of mass. So V would be an integral over the volume of the cylinder of density times G dx dy dz. And because we're assuming that the density of our cylinder is constant, and we know, well, so we could work that thing out, but sort of a nicer thing to do is, oh, sorry, I need a z in here. Yeah. Now note that the center of mass is 1 over the total mass of the integral over the body of rho sorry, that's not right. I need sort of coordinate. This isn't even a vector. I need like the r, the vector pointing, position vector of points in the body. And from that, if I take the z component of the center of mass, which we could call z sub g, is the integral. Oh, sorry. Just to make this clear, what I really mean is times the vector x, y, z. So it's the coordinate of each position in the body divided by the total mass. So which means if I take the z component of r sub g, call it capital Z sub g, it's exactly this times g. So the integral of rho z d, let's just write that as dv. So therefore, the conclusion is that the potential energy V is just mg zg, which is not surprising. It's a rigid body, so its potential energy looks the same as mgz, but with the z coming from the center, the component of the center of mass. In other words, it looks like all the mass is concentrated at that single point. It has that kind, the energy has that structure. Okay, the kinetic energy, that's very ugly. We saw this last time, so Ke, or call it T, is 1/2 m magnitude of rg dot squared, sort of our kinetic energy of the translation, plus the energy of the rotation, which we saw last time was 1/2 Lg dot omega. But Lg, I'll write it that way, Lg dot omega, Lg is Ig omega. So take vector times matrix dot matrix, that's the same as omega transpose Ig omega. Which is the same as, in this system, E3 is coming out of the board. And omega only has an E3 component with a theta dot, we saw last time. So this is like 0, 0, theta dot times Ig. Well, Ig has diagonal terms that I don't really care about. And down here, this I33, or whatever we called that last time, times a 0, 0, 0, 0, theta dot. And again, those terms aren't going to matter because I multiply this through and I just get I33 times theta dot squared. So we are left with the statement that the kinetic energy is 1/2, well, Rg, the motion is only along this axis, so that's just like an x hat dot squared. So it's 1/2 mass x hat dot squared plus 1/2 I33. And I33, I think we said it before, so if you do that integration over the cylinder, that comes out as ma squared over 2. But we also have theta dot squared is x hat dot squared over a squared from this. Let's put that here. Okay, so I have 1/2 m x hat dot squared plus 1/2 m plus another I3. Oh, sorry, there's another 1/2. Yeah, so this is like a 1/2. This is a 1/4 m x hat dot squared. I get a 1/2 there and a 1/2 there. So I end up with 3/4 m x hat dot squared. Yeah. So my total energy T E equals T plus V is 3/4 m x hat dot squared plus potential energy, which was mg zg Where is ZG in this picture? So this there is minus ZG, right? Z potential energy should be going up as I go that way. So this is minus ZG, which means that ZG is minus x hat sine alpha. The alpha there. So as it starts to roll, x hat increases, potential energy goes down. So we end up with 3/4 m x hat dot squared minus mg sine alpha x hat. And now we can check, is the energy conserved? So just take a ddt of this total energy. We get 3/2 m x hat dot times x hat dot dot, and then minus mg sine alpha x hat dot. Factor out an x hat dot from that. And if I've not made a mistake, that's 0. This is what x hat satisfies. So the quantity in the parentheses is 0, which means this is 0. So energy energy is conserved, and it's a kind of interesting conclusion. As I said all along, we've kind of had the notion that systems that conserve energy are ones where there's no friction, right? Smooth surface, no drag, etc. This is a sort of particular kind of energy. On the one hand, you might see from this equation that I've put friction in the system, but it's not slowing the cylinder down, right? This cylinder is accelerating under gravity, and nothing is slowing it down, right? So this is a friction that does no work in the system. Essentially what this friction is doing is just keeping that contact, sort of a little tiny bit of grippiness between the cylinder and the surface so that the cylinder actually rolls on the surface. So it's creating the rolling, but it's not slowing it down, which means that the total energy is indeed conserved. Okay. I think in terms of the sort of material we see in this course, these problems, they're probably the trickiest. Students often find this bit of the course the hardest. My suggestion is to go through this example quite carefully on your own and see that you can see each step that we've done. Part of it is defining, you have various frames going on, right? We have a fixed frame, we have a rotating frame. You have to be careful with right-hand rule and which torques are there, which torques are not there. But if you can make sense of this one, you can solve just about any of these rigid body problems. There's another problem in the notes, which I'm tempted to not put on the board because I want to make sure we have enough time to cover kind of sort of our last little topic. But there's a problem in the notes where we take the pendulum that we've had before. In the previous model where we had a pendulum, we put all the mass at the end. The sort of proper pendulum has mass distribution throughout. And just to kind of set it up just a tiny bit without going through all the steps. The idea of the heavy pendulum is that you think of it as it's a cylinder, but maybe it's a cylinder that's so thin that we treat it basically as a line that has mass, capital M, length L, and then we pivot it somewhere, say here, and then it rotates under gravity, or swings under gravity, right? And getting started there, again, is thinking about your frames. So you have one frame, which we keep sort of fixed. So maybe that's I, K. And that's our inertial frame, O hat. And then we have another frame, which is in the pendulum, which means we put a vector, say, call that E1 going along the pendulum, and E2 going that way. And just to maybe take that one more step, if I call that angle theta, what would we say? Sorry, I feel like you should use more colors here. Here's my pendulum. What would you say about the angular velocity in that setup? So E1's there, E2 is pointing there, so E3 is coming out of the page. As this pendulum swings back and forth, it is rotating only about that E3. So I expect omega to only have an E3 component. It's an angular velocity, so it's going to look like a d dt of theta. And maybe your only question is whether to say, is it theta dot E3 or is it minus theta dot E3? And again, the way to sort that out is to say, if theta dot is positive, do I get a positive right-hand rotation about the E3? Right? So I need to basically put my right thumb pointing in the E3. And I'm measuring theta as being positive here. So theta dot being positive means it's swinging that way, right? So if I have my right thumb oriented with the E3 and I curl my fingers in the positive, curl my fingers, that's a positive rotation about the E3, and that is indeed what happens when theta dot's positive. Okay, so that is the right thing. Of course, if you go through the details and you get something if I ended up with a minus sign over there, it's probably because I had a minus sign missing here. Okay. And then the other thing I'll say about this, in this problem, you have a choice. Are you going to do balance of angular momentum here? It kind of makes sense to do balance of angular momentum here. That's the contact point. But you could also do it here at the center of mass. And it's the same, it's getting that kind of picture straight, right? If I do balance of angular momentum at the middle point, then I don't have any gravity. Whereas if I put it at the contact point, then I do. And I think in this problem, it's actually more sensible to put balance of angular momentum at that contact point, the fixed point, and then the torque comes from gravity. Okay. Otherwise, you have to worry about sort of the reaction force at the pivot point, which is slightly less obvious. Okay, as I said, I'm going to leave this detail here. The notes, this problem is fully worked out in the notes, so try that one carefully. Try this other one carefully on your own. And I want to move on to our last topic of the course, which has been sort of hinted at a number of times, but now let's work out the details. Newton's laws in a non-inertial frame. So, for instance, you might say, here's a scenario. Imagine that we are in a train generally accelerating, but maybe the train's going around a bend, and I do an experiment. I toss a coin, I don't know. And I want to work out the motion of the coin, and I'm in the train, so I'm in this non-inertial frame. And the question is, how do I adapt Newton's laws so that I can work out the trajectory of the coin? Okay. We've sort of already started the key to this calculation before, but let's draw a picture. So here's a fixed frame, an inertial frame, O hat, as we've been using. And here's our train track, I guess. And here is where we are. Call that vector x hat. And then I have my non-inertial frame, which I might call, doesn't really matter, E1, E2, E3. And then I have some object, say, located here at position vector r, which I measure from this origin, which is our O, our non-inertial origin, and I measure it in that basis, the moving basis. Okay. So our starting point, as we've seen before, is I can write big R as x plus, what's an x hat? Let's not have a hat here, just call it x. X plus little r. And little r is the sum of r sub I, E sub I. So I want to add it to the picture. Big R is the sort of vector from the inertial frame to the point. And dr dt, which is what I mean is the sort of true velocity, a velocity measured from the inertial frame. So let's write that notationally as dr dt measured in s hat. is dx dt measured in s hat, plus, when I come to taking a derivative here, as we saw before, taking a derivative here, I get one component that goes to the r sub i's. So I get a sum of r sub I dots ei. But the sum of r sub I dot ei is what this person measures as the velocity of r, right? So that's plus dr, the little r dt, according to the s. Plus, those e's are also functions of time. And when I take the dei dt, I get this omega cross e sub I, right? Angular velocity for the frame. Capture the rotation of this frame with respect to that one. So there's a single omega. I pull that single omega out of the sum, and I end up with an omega cross r. So my extra term here is plus omega cross little r. Okay, we did that calculation before, but now I want to go to Newton's second law. Newton's second law means I need to talk about accelerations, and to talk about accelerations, I need a second derivative. Okay. So we need to be careful here. Let's see if we can take a second derivative. So therefore, the acceleration measured in s hat, let's call that a hat. A hat is big R dot dot. And it's just taking another derivative of each of these terms. But I have to be quite careful because there's really three terms here. And each of those terms involves e sub i's. So I need to be careful. I'm picking up extra omegas at each step. So on the one hand, the x is really just measured from here. So if I take derivatives with respect to t of that x, it just carries straight through. So I get a d squared x dt squared in the s hat. And if I think about taking a time derivative of this guy, it's really just doing this exact operation over again, right? Take a time derivative. One of those time derivatives goes straight to that term, and then the extra time derivative comes from the e sub i's, which means I get an omega cross that term. So I get a d squared r dt squared measured in the s plus an omega cross dr dt measured in the s. And let's just use some colors to sort of keep track of where terms are coming from. So that single term there, taking the d dt, has produced this and that. And now it's going to be the same thing here, but because this is actually two terms, I have a sort of product rule plus this extra term that shows up each time. So we get a plus d. So if I just think about taking the time derivative to the omega and then crossing whatever I get with r, I get a that doesn't seem right. Plus an omega. Oh, surely that's something wrong in my notes. S hat. Why have I written that? Cross S. Let me write what I've got here. I've confused myself. Right, so when I take d dt of this guy, I should get a omega cross dr dt in the S plus an omega cross the omega cross r. Tangled myself up. Can anyone see why I've got a d omega dt in the S? Typo in my notes. Or oh, okay, sorry. I'm taking it one step at a time. I've confused myself about this term here, but I'm going to keep going so we don't just stand here for 10 minutes staring at the board. D omega dt in the S hat is d omega dt in the S plus an omega cross an omega, which is 0. By definition, cross product. So if I define let's call it capital A as d squared x dt squared measured from the S hat. So that's like the acceleration of the moving frame, right? So that's acceleration of the S. And let's call little a d squared r dt squared measured in the S. So this term here, this is what the person on the train measures as the acceleration. Then we can just shuffle things around and we get that little a, the acceleration in the non-inertial frame is a without the hat, or sorry, a with the hat. I'm going to do the other way around. So a with the hat, the sort of proper acceleration is the non-proper acceleration plus capital A, the acceleration of the frame, plus we get 2 copies of an omega cross dr dt. In the S, and we get a d omega dt in the S plus an omega cross r. So therefore, Newton's second law in the S looks like m, just bring in a mass, m times non-hatted A is F, and by F I mean the sort of whatever external forces there are, so that F is the same as m times A hat. In other words, this bit is Newton's second law sort of proper in the inertial frame, and then we have to get all these extra terms, which I'm going to lump into a big bracket. So you get, effectively, I need to bring all those terms to the other side. So that's minus m times capital A minus 2m omega cross dr dt in the S minus in m d omega dt in the S minus in m omega cross r. Okay. So there's a lot sitting there, and what it means is that I have to adapt. So I'm in the train, I measure this, I want my acceleration times mass to balance the forces, and as well as the sort of force that I know about, I have all these extra forces that just come from the motion of the frame itself. So those are all called fictitious forces, and they have specific names. So if we label, of course, that one's just coming from the acceleration of the frame. This one is called the Coriolis force. Which you've surely heard of before. So these forces exist. If I think about experiments on a large enough scale, the rotation of the Earth introduces these forces. The second, the m d omega dt, is called the Euler force. And this last one is called the centrifugal force. Okay. So I want to see if we can work through a quick example. Make one quick note, though. Made this point a few times. It's up to us, right? We choose where we put a frame and how we describe a system. So for instance, we pick the S frame. So for instance, let's suppose I have something just driving around, a car going around a circle. So there are kind of two options that make sense. One, if I'm doing a moving frame. One is I could have my S frame here, and then the frame itself just rotating as the car rotates. So in that version, I'm choosing x to be 0, right? Which means that capital A is 0. I could do the exact same problem where not only where I put my frame at the track, if you want. So now the frame is rotating and moving. So x hat is none, so that's my S. Of course, there has to be a consistency. If you work through the equations, you'll get the exact same answer in the end, but those terms come out a little bit differently, and it's a choice, right? Of course, we don't have to work with moving frames at all, but there are problems where working with the moving frame can be quite convenient, and I just want to start to set up an example. So this will be our last example of the course. And the system we have in mind is a bead on a rotating hoop. Okay, so the picture is, I have, let's call that the I and the K, and I put a hoop of radius A centered around the origin and in that plane. So J is going into the board. And what I'm going to do is I'm going to take this hoop, I'm going to put a bead on it. So put a bead somewhere here. And the bead is going to sort of slide freely, frictionlessly around the hoop. It's going to feel gravity, but I'm also going to spin the hoop around the k-axis. I'm going to rotate the hoop around the k-axis, which means I'm going to have an angular velocity. Well, let's just say it this way. Rotate the hoop around the k with constant angular velocity. Let's call that scalar omega. Okay, now I want to describe the trajectory of that bead as it rolls around, slides around the hoop. So we could do this in the non-inertial frame. If I were to do this in a non-inertial frame, it's really just an example, a slightly complicated example of a constrained motion. Right? I have a three-dimensional space, but I'm restricted to this two-dimensional, really one-dimensional, because I'm on a curve. But the curve is rotating, is the complication. Right? So if I were to do this in the non-inertial frame, I would use spherical coordinates. I would write the position vector r as a sine phi cosine theta, a sine phi sine theta, and a cosine phi. So phi being that angle, and theta being the angle around the ij plane. And then we could write Newton's second law, take a bunch of phi dots and theta dots, and then what we need to use is that theta dot is actually given to us in the problem. It's fixed as omega. Right? Okay, it's not very nice because I'm in spherical coordinates, got lots of sines and cosines. If I were to do this same problem in an inertial frame, non-inertial frame, what I can do is I can let S rotate with the hoop. So in my S frame, let's call this the E1 direction, and this the E2 direction, and this frame is rotating with the hoop, which means that I don't have two variables to describe the location of the bead, I just have one. I'll put the bead here at an angle, again, phi. And so in that description, the position vector of the bead is just 2D polar coordinates, which is like a cosine phi E3 plus a sine phi E1. And therefore, dr dt measured in that frame is very easy because I just have phi's there. So I get minus a phi dot times sine phi E3 minus cosine phi E1. In other words, there's no E3 dot, E1 dot I worry about at that stage. And I can take a dr, I can take a second derivative in the s, and it's again just going to get a phi dot dot and some back to sines and cosines. And what I need to do to work out the motion of the bead is I need to solve m d squared r dt squared in the s as minus mg E3, right? Gravity's, sorry, this should be, I've used 3's here. That's a 3. I mean that. Gravity's, that's the sort of force I know about, plus all these fictitious forces that come from the fact that my frame is rotating. So plus, be careful, there's a normal reaction force. There's minus 2m omega cross dr dt in the s. There's minus m d omega dt in the s. And there's minus m omega cross r. There's a kind of a no free lunch principle, which is that if I do it in the inertial frame, I don't have these extra forces, but I have to deal with the kind of ugliness of spherical coordinates. Say, okay, switch to the non-inertial frame. I don't have the ugliness of spherical coordinates, but I have to worry about these extra terms. Right? So these aren't too hard to work out. So I've called that term 1, term 2, term 3. All you really need to do is use the fact that omega is given to us as omega E3. Which means that term 2 is immediately 0 because this is constant. Term 1, all I need to do is take my dr dt expression, which has an E3 and an E1, and cross it with an E3. I get, pretty quickly, I get an E2 term out of that. And then this term, I do an omega cross r and do one more cross omega. Again, it's just working within that E1, E3, E2 basis. So those aren't too hard to work out. I think I will leave the details here so that we don't run over time. You can see all this details worked out in the typed notes. It might seem, as I said, that we've complicated things by adding all these fictitious forces, but as I said, it's in a way, especially if the rotation is constant, it's not that hard. You can work out these extra terms and not having to worry about all the extra product rule terms that come from the ugly coordinate system. Sometimes it's worth it. Okay, I think we should stop there just to give kind of a very final thought, if you want, on this course. Draw a sort of quick picture, if you want. So we have we've spent 16 hours sort of assuming that Newton is true, right? It's Newton's second law, first law, third law. That's our baseline assumption. Use geometry, use various tricks, and see how far we can go. We acknowledge from the very beginning that this is not a truth of the universe, but more of an approximation. Nevertheless, these ideas are really fundamental for many, many, many other fields. So on the one hand, if you start looking on smaller scales, at some point you see that the same ideas hold, but things become probabilistic. So if you're thinking about the mechanics of a polymer or a strand of DNA, many of the same ideas are there, but things become probabilistic. You don't have deterministic, you have probabilities. You have approximation like that. And of course, if you keep digging down smaller and smaller scales, you get to quantum mechanics where things are entirely probabilistic. Nevertheless, many of the same ideas, principles exist there. If you go to the other direction, you go to, say, larger scales, larger and faster, you again see that Newton's laws are no longer true, and you get into the area of Einstein and relativity. Nevertheless, I don't think you can really appreciate and understand relativity unless you've got that basis there and sort of understand the corrections that Einstein was making. These things about Galilean transformations and absolute, what does it mean to be an inertial frame? I have to be able to measure that. Einstein sort of does away with that as a starting point, and you see many of the same types of developments. And then there's still this ground in the middle. So if I'm still sort of staying at the everyday scale, if you want to call it that, the extension of Newton on the everyday scale has many, many sort of current and relevant fields. So for instance, there's sort of general field called continuum mechanics. So fluid mechanics, elasticity, things like that. These are really extensions of Newton's ideas to, say, non-rigid bodies. If my body is allowed to deform, how do I extend Newton's ideas? But still within sort of taking Newton as truth, just extending the ideas in many nice ways. You also have things like electromagnetism, which kind of fits across those scales. And maybe one other thing worth noting is, dynamics, the dynamics bit of this. If you're less worried about the physical interpretation, the other place where this work goes very nicely is into nonlinear systems. And then you get into areas like chaos, bifurcation theory, etc. Those are physically motivated, but it's more taking the idea of things like Newton's equations, but with long or very complicated nonlinear terms, and then what does that imply about the dynamics? There's courses in this building basically across that spectrum, and if you've enjoyed this material, you'd probably enjoy some of those extensions. If you haven't enjoyed this material, sorry, but I hope you at least maybe look at things in a slightly different way. Sort of walking down the road and you see like a skateboarder do a cool trick, you say, good use of the reaction force, those forces are everywhere. Those force balances are in everything we do. And yes, let's stop there. And thanks for your attention. Hi everyone. So I just want to clarify a point of confusion towards the end of the lecture. So we were computing derivatives in non-inertial frame, and I had this expression. So our capital R is position x plus little r, and little r is the position vector in the non-inertial frame RIEI. We were taking derivatives, so dr dt, sort of the velocity you would measure, which is in the s hat, the inertial frame, picks up the derivative of the x in the s hat plus r, the dr dt in the s plus an omega cross r. This is what we had defined previously, omega being angular velocity. Then we took a second derivative. We want r dot dot. So that comes straight through to the x. And then when you apply it to this term, you get the same structure where there's a second derivative in the s plus an omega cross that term. So that's the dr dt in the s. And then we need to apply that to this term, which is going to involve a derivative on the omega and a separate one on the r. And in the lecture, I wrote down this term with the omega dt s hat without an r there. And then I stared at it, confused for a while. And effectively what had happened is that I had the same typo written 3 or 4 times in my notes, and I just doubted myself and thought that I was missing something about why that omega would be sitting on its own. So because it's crossed with r, that r comes straight through to here. This is what I should have had written on the board. And then that's in the s hat frame. And then we wrote that if you take derivative in the s hat frame of omega, you get the derivative in the s plus an omega cross omega, which is 0, which means that s hat and s derivatives are the same. So in fact, we can do that. And then these last 2 terms were correct as written. That's just taking
that same rule applied to the second term and with an omega cross. So everything else carries through as we had written it in the original board. Everywhere you see that d omega dt in the S, you just need to add the cross R. And that's that. Thank you.